All right, hi everybody. So we have been talking about creep. So that's chapter 13 in the textbook. And it is distinct from everything that we've talked about so far because it's a long time process. And it's a combination of time and elevated temperature. And it causes elongation that's not considered a yield and it's not considered a fracture. But it can result in a failure if there is significant enough elongation. And so I wanted to make sure that we were incorporating all of the ideas that we know, because even though the text gives brief treatment to some of these things, the actual usage of them can be a little bit more tricky. So today I'm just going to do example problems. And these are all problems that are in the problem set at the end of chapter 13. So today's lecture should help you with the final problem of the problem set and should give you a better understanding of how to do some problems and some content that may be on the final exam. So the first problem I'm going to do is problem 13.6. And it states this: a sand cast aluminum alloy creep tested at 600 degrees Fahrenheit results in the data shown in figure 13.6c, curve B. Okay, so we're going to stop there for a moment. And so you can see on the screen, this is figure 13.6c. So it's the bottom half or the bottom third of that figure, and curve B. So that means it's the top curve that you see here on this slide. So I'll just sort of draw with red along it there. So it's this top curve here, and we'll use the scales at the left side. So this is time in hours across the bottom, and then creep inch per inch on the left side. So that is an elongation in inches versus the initial length of the specimen in inches. So it says that's the data that came from this creep test when it was subjected to a stress of 10,000 psi. So this is just a tensile stress and hold, right? A solid square support bracket of this material. So now we're not in the creep test mode, now we have our own part, is inch by 4 inches long and is subjected to a direct tensile load of 10,000 pounds. So same conditions that this thing was creep tested at. So we can sort of just draw a picture, right, of sort of a rectangular prism with a 4-inch long side and then a 1 inch by 1 inch across the bottom. And if it's under 10,000 pounds direct tensile load, the cross-sectional area is 1 inch squared, right, so that we know that the load is 10 KSI. Okay, so that's the setup for the problem. And then it gives us a cycle that this thing undergoes. And the cycle is a temperature cycle. Okay, so there's some processing which happens around this bracket. And I'm going to make a chart on the next slide. And they tell us that even though it was creep tested, so tested, I'm going to write at the top, 600 degrees Fahrenheit. Maybe they only had like one creep test they could do, and then they said, okay, go predict. But the cycle is actually 380 degrees Fahrenheit for 1,200 hours, 600 degrees Fahrenheit, so that was our test temperature, for 2 hours, and then 810 degrees Fahrenheit for 15 seconds. Okay. It says, how many cycles would you predict could be survived by the bracket if the design criterion is that the bracket must not elongate more than 0.1 inches? So elongation is less than or equal to 0.10 inches. Okay, so this is all the information that we're given. And we know that creep is a time and temperature process, And so those effects can be combined. And I mentioned in the lecture that I didn't see any example problems that had those parameters that included time and temperature, but actually this problem is solved with those parameters. So we are going to use that in order to do that. We need to calculate a few more things before we can really get going here. And so they've given us elongation, and they've given it to us in units of inches, so we have to calculate the maximum creep strain. So we can say delta creep, right, has to be less than or equal to 0.1 inches divided by our specimen length, 4 inches. So 0.025, 2.5% creep, so fairly high. We calculated the nominal stress, and we're going to have to use some sort of cumulative creep model. So we have time, we have temperature, and we know that the stress is constant, right? So the stress is a constant. Okay. So that's what we know so far. And so let's use one of these parameters, like the Larson-Miller parameter, to give us sort of a variable, like a state variable. And then we will use that to translate between temperature and time. Because we know that we have data at a certain temperature, but we need to know how long things are going to last at other temperatures. So if we can turn both those knobs of either temperature or time and keep that parameter the same, then we can put together some sort of a lifetime for this part. So that's what we're going to be doing. So we are going to use the Larson-Miller parameter. It's the first one that's in the book. Okay, and so it states that this parameter stays the same for reasonable combinations of time and temperature over sort of measurable ranges. So we had temperature, which was represented by theta, plus 460, where this is in degrees Fahrenheit, times a constant plus the log base 10 of the time, where C is a value of 20 usually, is what the book tells us. And this time is in hours. Okay. So we have some data. So let's go back and look at what this parameter is if we just calculate it based on when the sample failed, right? Because that's our bounding situation, is when the thing failed. So if we go back and look at this, we can see that it says specimen failed up here at the top. And so if we look at that point where the specimen failed, we can read off, or at least if you have your textbook, you can read off, as it's tiny lines here. It's about right here. So when we're in a log scale and we have those minor lines, we can count by hundreds in this case, so 2, 3, 4, 5, it's about 600 hours. And at that time, the specimen is 0.020304, right? So that's too high for what we were given, right? We said our creep strain was limited at 0.025. So we can also go back and say, okay, here our creep strain is about right here. We can go over, and then we could read off the time from that as well, right? We can use either one of these to calculate what this parameter is, and the points are very close on the curve. So I'm just going to use 600 degrees and 600 hours to have that be our Larson-Miller parameter that we're going to use going forward. Okay, so P is equal to, we had 600 degrees Fahrenheit is our test temperature, and then we have 20 plus the log of 600. And so if we calculate that, we just get a number. I got 24,140. Right. And this is just, it's kind of just a parameter, right, that tells us how these things go together. Okay, so now we have some different temperatures. So let's calculate what the failure time would be for those other temperatures. Question here.
What's the 20 on the constant?
The book just tells us that constant is usually taken to be 20. So I'm assuming for different materials it would vary a little bit, and there are probably lookup tables for that. We're just going to use 20. Yep. Okay. So we would expect now, just intuition check, right? If we're at a lower temperature than the test temperature, then this sample should be able to last a lot longer. And if we're at a higher temperature than the test temperature, it should last a shorter amount of time, right? If it's a time, temperature, superposition type thing. Okay. So if we then take the Larson-Miller parameter equation up here and solve it for time, we come up with T is equal to 10 to the power P divided by theta plus 460 minus 20. So all I did was take the inverse of that log 10. Okay, so we'll make a little chart on the next slide that tells us what could be our expected life at those, if it were tested at those temperatures. Right, so we'll have theta, and then we'll have our time in hours. We had 380, 600, and 810. And I solved this, so I got for the 380, I got 5.54 times 10 to the 8th hours, right? So we said if we tested at a lower temperature, it should last a lot longer. So that matches with our intuition. I used 600, so we get 600 out to calculate it in the first place. And then at 810 degrees Fahrenheit, I calculated it would last 0.103 hours, right? So that's about 5 minutes, 6 minutes, right? So that's not very long. Luckily, we said that we only had that temperature for, what was it, like 15 seconds, right? So that's shorter than that lifetime. So that's good. That means this will last longer than one of these thermal cycles. Right? Okay, and so what we can do to solve this is basically just say how much, which of these is the limiting factor, and then use that to calculate how many cycles we can get, right? And so for the first one, our time that we need is, I think, 1,200 hours. So if we take 5.54 times 10 to the 8th, and we divide it by 1,200, oh, I have the inverse written down here. So if our time is 1,200, I did it in sort of a cumulative damage type way, but I can do it the other way also. Okay, 5540. Right, so how many of these could we get? I'll call that N. About 462,000. Okay, not bad. So the time we needed at 600 degrees was, I think, 2 hours. So that's 2 divided by 600. No, 600 divided by 2, 300. Okay, so if we only had those two, that would be the limiting one. And then the other one is we need it to last for 15 seconds, right? And we need that in hours. So we got to do 60 seconds per minute and 60 minutes per hour. And we get 0.103. Is that right? No. Um, yes, that sounds better. 4.2 times 10 to the minus 3. So like 0.0042. Okay. So our time is 4.2 times 10 to the minus 3. So if we take 0.103, divide it by that, right, we can do that 24 point something something times. Right, so that's the smallest number of times we can do that before we would expect a failure based on the creep strain. Okay, and so we can round that down to 24, right? So we can do this thermal cycling from 380, 600, 810, 380, 600, 810, 24 times before we would expect this thing to fail. Okay. And so this is just a very kind of like back of the envelope way of calculating this, right? Because we only have one curve, we don't know what happens truly at these other temperatures, at other stress levels. This is all the information that we're given, so this is the best that we can do. This does not take into consideration any sort of accumulative creep strain, right? So all we did was just say that, the highest, most limiting phase is what determines how many cycles we can go through, right? We could do this in some sort of a cumulative fashion, but the book doesn't tell us specifically to do that. It gives us a different way of doing it, a cumulative way, if we have more curves. And so if you wanted to do this in a cumulative way, you could, where you calculated not just how many cycles this one would last, but you said if the time to take one cycle is X amount, like 380 degrees Fahrenheit for 1,200 hours, you could calculate the expected creep strain from that one phase. And then 600 degrees Fahrenheit for 2 hours, and then the creep strain from that, and add it together. And then the high temperature one, the 810 for 15 seconds, and then add that creep strain on, and you could sum up all of the creep strains until you get up to some failure. And so if you do that, you come up with 22 cycles instead of 24. So really, that high temperature 15 seconds is the one that is limiting the creep lifetime of this part. Okay, so that's that problem. Questions on that? It's pretty straightforward. Yes, question here.
What was the indicator to use the Larson-Miller parameter, and why did we use the 24,000 again? Like, what was the giveaway or the indicator in the problem that would do that?
So two giveaways. The first one is we're only given this one curve, right? So all we know is the specimen failed at that top point. And so if we want to avoid failure and we know a limiting strain of 0.025, then we use that. We say we calculated the parameter and we toggled between time and temperature to get how many times we could do that. So the chart, the fact it only has one line, means we can't use the cumulative theories that I'll go through on one of the other problems. Like we can't jump back and forth between different stress lines and temperature lines. So we only have the one. So that's kind of the one tell. Yep. And then there are two parameters in the book. There's no tell for which one to use. So whichever one you're either told to use or use the simplest one. That's what I did. Right? So for most engineering problems, use the simplest one that is accurate enough. Right? So, okay. So the next problem I wanted to do was 13.9. So let me get past this one. Okay. So 13.9. It says this: a cylindrical pressure vessel of nichrome steel has closed ends and a diameter of 10 inches. All right, so I'm just going to draw like cylindrical pressure vessel here, nominal diameter 10 inches. The tank is to operate continuously for 5 years at a temperature of 850 degrees Fahrenheit. That is a lot of energy to keep that thing at 850 degrees Fahrenheit for 5 years. Okay, under an internal pressure of 10,000 psi. If a safety factor of 1.2 is desired, so n equal 1.2, and permanent deformation must not exceed 3%. So creep strain should be less than 0.03. What should the minimum thickness of the cylindrical pressure vessel wall be made? Okay, so there's a wall thickness here, and that's what we need to solve for. Okay. This problem should bring back, all of the good memories of thinking about pressure vessels under static yielding, under fracture, plastic deformation, and biaxial state of stress. So you should kind of have those things in your mind. And we've written down everything we know, okay? And so we must have something in the textbook that is going to give us the properties of this nichrome steel so that we can calculate what these creep strains will be. And then we'll take into consideration the biaxial stress state as well. Okay, so this is just one short section of the book with some modified equations in it, and so we're just going to apply those and see. So we need to do some preliminary calculations. Give me 1 second. I think there's a difference in units here, so I want to make sure I do the right thing. We'll come back to the time in a moment. We wrote down everything else, and so we have to, at some point in this problem, relate stresses to strains, right? And so let's go ahead and calculate our hoop stress and longitudinal stress in this pressure vessel, since we have at least some of the parameters. We have the diameter and we have the internal pressure, right? So we're going to say that the hoop stress, and this is going to be not an elastic stress, and so we'll use the prime just to indicate that this is a non-elastic stress. And so it's going to be the internal pressure times some sort of a nominal diameter divided by 2 times the thickness T. So we have some of those values. We have the internal pressure, 10 ksi. We have a diameter, and we're just going to use 10 inches for now on that one. And we don't have the wall thickness yet, so we'll just leave that as a variable, T. So our expression for the hoop stress is going to be just 50,000 divided by T. And that's going to be in PSI. So it's 10,000 times 10 divided by 2, 50,000. The longitudinal stress, or the axial stress along this pressure vessel, is half of the hoop stress. Whoops. So it's just P times D divided by 4T, or half of the value that we already calculated. So it's 25,000 divided by T. Okay. And these are the principal stress directions. If we assume that this is a thin-walled pressure vessel and there's no strain in the radial direction, like compressing the wall thickness, but rather there's plane stress going around in two dimensions. So that means that these directions are also corresponding to the principal strains, right? So there will be a a strain along sigma 1 and sigma 2, right, corresponding to this, or sigma 1 and sigma 3 or something like that, right? So our textbook tells us that we can derive equations for multi-axial creep. And I think I went through this a little bit in the last lecture, but this is equations 13.38 to 13.40. And it tells us that we can relate the creep strain, the first principal creep strain, to the first principal stress. And then it has all of those alpha and beta parameters, right? So I'm just going to write them out here because one of them will go away. N minus 1 divided by 2 times 1 minus alpha over 2 minus beta over 2. All right. So this is the first principal strain, and we have a lot of things in here. Okay, so let's just break it down so that we all know what's what. So B, this is a coefficient, right, for the log-log stress time creep law. Come on. Log-log stress time creep law, right? We had B and we had N that we could describe that creep with. So N also comes from that. So I'm going to draw an arrow from here and also from here. Okay, so all those exponents are going to come from basically a lookup table and that coefficient B for this nichrome steel at 850 degrees Fahrenheit. Okay? And then T is our time. And we want to make sure that we're using time in the right units for this equation with the log-log stress time creep law, which I believe is in days in order for this to work out. And then we have our first principal stress, right? And we know that from the, go green, this first principal stress, we know that from our hoop stress equation. Okay. And then these alphas and betas relate to the ratios of stress, right, in a different direction. So alpha is, right, sigma prime 2 over sigma 1 prime. And in our case, that's 0.5 because we have that cylindrical pressure vessel. And beta is, if we had a direction with a third principal stress, we would normalize that one. But in this case, beta goes to 0. So you can see now that if we have a limiting shear strain here, right, that had to be 0.03 or less, then the only thing we don't really have is that thickness in the hoop stress. That's the only remaining variable here, is that thickness in the hoop stress. So we will basically just plug everything else in and solve for that. Okay. So I'm going to write some values down for these. So in table 13.4, for this nichrome steel at 850 Fahrenheit, we can find that B is equal to 10 times 10 to the minus 20 power, and N is equal to 3.0. Okay, so that gets those two things out of the way. Our time in days, we had 5 years. Right, so 5 years times 365 days. All right, I had this in my worksheet, but not in the notes here. 5 times 365, 1,825 days. Okay, so that's what goes in there. We already have N. We're going to cross off any term that has beta, because it goes to 0. And then we can think about what our alpha will be here. So the final term, the one with that's in the dark blue here, is going to be 1 minus 0.5 divided by 2. 0.5 divided by 2, 0.25. 1 minus 0.25, 0.75 is this final term here. And then we can also take 0.5 squared minus 0.5 plus 1. And I believe we also get 0.75 for that. All right. And let's take a look at that exponent on that large term. So it's n minus 1, that quantity divided by 2. So n is 3 in our case, so 3 minus 1 is 2, divided by 2 is 1. So this exponent goes to 1 as well. So there's a lot of things that simplify out here. Okay, so let's plug that in and see what we get. So first principle strain, right? We have 10 times 10 to the minus 20 times our time, 1825, times the hoop stress, 50,000 divided by t. And that is to the third power times 0.75 to the first power times 0.75. And if we plug in for delta 1 here, 0.03, right, we come out with 0.03 is equal to 0.00222 times t to the minus third power. So I just left everything on its same side. And so that's the equation that we're solving. And I forgot one thing in here to get that number. So we had a safety factor of 1.2, right? And so if we think about our prior use of safety factors, they usually go on a stress, because that's usually what we're using as our framing for failure criteria, right? For yielding, we do that. For linear elastic fracture mechanics, we do that. And so we can do that in this case. And so if we multiply our hoop stress times 1.2, we get 60,000 up here. So that's what I used in my calculation to get these numbers. We'll talk about that more in a minute. And so if we then solve that, we can flip things around on the other side. We get t cubed is equal to 0.739. T is equal to 0.904 inches. So this is one solution to this problem. And so that's kind of taking our historical precedent. So this assumes a variety of things. So what it assumes is that we apply safety factor to stress. It assumes that delta 1 is our highest strain. And so that's the only one that matters. That's the only one we're comparing. And that all of the other assumptions that went into this equation are also holding. Okay, so if we do that, we get this thickness of 0.9 inches. Like, that is a very thick wall on a 10-inch pressure vessel, right? So if the diameter is 10 inches, that means 2 inches of that is eaten up with the walls. And this really can't be considered a thin-walled pressure vessel. So for a thin-walled pressure vessel, you really need the thickness, the wall thickness, to be less than or equal to like 0.1 times the radius or something like that. There's like thresholds like that. I think you can look it up in the book as well. And so this does not, so it does not align with a thin-walled pressure vessel. Okay, so if we really wanted to use these assumptions, we could go back and we'd have to modify our expression for the hoop stress, because the hoop stress that we used was for a thin-walled pressure vessel, and so it would be a more complicated expression. So we should go back and then and redo the problem, because our answer does not align with our assumption of a thin-walled pressure vessel. Okay, so that's one solution to this problem. Okay. And so there are a variety of ways that we could modify this to come up with something we think is a better approach. And so I'm not going to go through all of those, but I am going to mention what they are. And you could probably see them based on what I've listed out here, right? So the first thing that we could do is we could apply the safety factor to our creep strain instead of a stress, right? So we're assuming that our stress doesn't change. It's the pressure vessel is pressurized, stress stays the same. What we have is constant stresses and high temperature, right? And so we get this creep elongation, and that's what leads to our failure. And so if we're using our safety factor on our failure criterion for this specific problem, that's the creep strain, right? So you could come over here, right, and divide the allowable creep strain by 1.2, which then drops our allowable creep strain, right? If we do that, however, and we keep all the other assumptions the same, our wall thickness has to increase to compensate for that, right? So if the hoop stress is what's leading to the creep strain, right? So that means the pressure vessel is stretching in the hoop direction, right, due to this creep strain. Then if our allowable creep strain is smaller, then we have to have thicker walls, right, to prevent it from doing that, to last the 5 years. And so that further violates some of our other assumptions. Okay? The other thing that we can do is calculate more than just the first principal strain here. So in our textbook, they give us expressions for delta 1, delta 2, delta 3, okay? And so we could calculate that, and we know that all of those strains have to sum to 0, right? So that we are not having a volumetric change. However, we talked a little bit about how we assume that there's no volumetric strain for creep, but if creep is the mechanism of creating microvoids, which then coalesce into macrovoids, then the change in volume assumption sort of breaks down, right? And so if you do that, you will find that you'll have 2 out of the 3 of these will be non-zero, and you could use an effective strain, right? So you could calculate some effective strain that's a function of all of these 3 principal strains, and then use that compared to the maximum strain allowable, right? So then you'd have a combination of directions. And so you can do that as well, but if you now are taking into consideration 2 directions of stress, now we have 2 directions of strain, and we have to then, again, have a thicker wall. So what we really find with this problem is that no matter what our assumptions are, we can't use the expressions for a thin-walled pressure vessel. So I think the problem is an interesting one, and I think maybe the textbook tried to use like sort of the materials properties they had on hand and a feasible problem, but I would say it breaks down in some serious ways. So questions on that problem?
What was the effective strain look similar to the principal strain? That's one.
So in this case, when I talk about some equivalent strain, the question is that like a similar expression to delta 1? It's not. So what you can do is, if you're switching from a stress-based failure criterion to a strain-based failure criterion, you can sort of express an effective strain as like a von Mises strain. And so you can say some sort of an effective strain is an expression like this, which is a combination of the principal strains. I'm going to go, this is just, this is not even suggested in this chapter of our textbook, but I found it in a different text. So you just do the sum of all the differences like this. The differences squared and then take the square root. So it's just, yeah, so in this case I wrote epsilon, but that would be the deltas that we calculated, yeah. And so it's just it's a combined term to represent the strains in multiple directions, like some effective strain. Because if we just sum the strains, they sum to 0, so that doesn't help us, right? So that's what I meant by that.
And you would only do that when the delta 1, 2, and 3 would be non-zero, right? Well, sort of by definition, there has to be more than one that's non-zero, if there are any that are non-zero, because they have to sum to 0. So if I have like delta 1 is equal to, like I think I had, I don't know, I didn't even recalculate the value, but whatever it is like this, then I have to have either delta 2 or delta 3 be negative 0.002 in order to satisfy just the conventions of how we use it. Yep. Okay, good questions. All right, the last problem I have prepared is, I think it's 1311. I don't think I wrote down the problem number here. But it talks about the cumulative strain theories, and it gives us a chart, and then asks us to use the 3 different theories. So they had the time hardening rule, strain hardening rule, and then the life hardening rule. All right, so let me go forward and find my chart here. Aha, okay. So they give us this chart for alloy X, right? That means we don't actually have to relate it back to the real world, right? But it could be any alloy. And they have done a creep test at 4 different stress levels and provided us the creep strain in inch per inch as a function of hours. These are both linear scales. So we have time in hours from 0 to 80, and we have creep strain from 0 up to 0.01, and we are told that this was done at 1200 degrees Fahrenheit, so really high temperature. And so we are asked to calculate what is the total creep strain, I'm going to call it delta, for a series of stress loadings, right? So this is kind of going back to when we were doing the rain flow and we had different amounts of stress applied for different types of times. We're not going to do any rain flow here because we are given that in sort of the first phase, it's at 1,000 psi. So that's the first curve, 1,000 psi for 10 hours. And then it just goes up incrementally, like to curve. So it's fairly straightforward. So it's a good problem for comparison. Then it goes in the second phase to the second curve for 20 hours. Then it goes to 3,000 psi for 20 hours, and then 4,000 psi for 10 hours. And that's one sort of cycle of stress loadings that a sample experiences. Then we are assuming our sample is the same geometry as this one. So this is a constant temperature situation, but now the stress is changing in time instead of the temperature. And we have all of these nice curves, okay? So the first method we're going to use is the time hardening method. which means that time is continuous. And for each time we add up, we go like the 10 hours, 20, 20, 10, and then again 10, 20, 20, 10. And we assume that time is continuous, but we look at the change in the creep strain on each curve for those times, taking into consideration its time history, right? So it's called time hardening because time is continuous and we care about the time history. We don't care about the strain history, we care about the time history, okay? So I'm going to draw some lines on here to show how we would go through this for time hardening, right? So the first phase is the bottom line, 1,000 psi for 10 hours. Well, 10 hours is the first number we're given there, so we just follow the bottom line out to 10 hours here. And then we calculate the change in the creep strain. I'll just draw it as like a red bar here for that first phase. So it's pretty straightforward. It's close to half the mark up to 0.002, so I called it 0.0008, right? Or 0.8%. 0.0008. So for the first phase, that's what we got. Because this is time hardening, when we move to the second phase, we're going to start at 10 hours again, but we're going to jump up to the next line of stress because our second phase is at 2,000 psi. So we jump straight up to that line, and then we go 20 hours on that line. So we can find where 30 is, and then we go along here. And our creep strain is now the change from where we ended up to where we started on that line. So it's this red bar that I'm drawing here. So you can see that it's discontinuous, right? And so that's the drawback of this technique, but it's continuous in time. So that's the advantage, and it takes into consideration the time history because it's already been under some stress for 10 hours, right? Now it's under this next stress for 20 hours. So if we calculate the difference there, if we go like well, I didn't draw straight as I did in my notes earlier. So I said it went to 0.003, and then I subtracted off 0.0015. So I said for the second phase, it was like 0.0015, right? And these are approximations reading off the chart. Okay. Let's go to our third phase, so 3,000. We start at the 30 hours, so we start here. And we go out to 50 hours because it's 20 hours again. And so then we come across, right? We sort of calculate our third increment of creep strain here. And I think I came up with slightly larger than those tick marks. So I had 0.0011, right? Approximately 0.001. And then we do the same thing for the fourth one, but now we're only 10 hours. So we just go 50 to 60. So 50 to 60. We come over here. And you can see that the change in the creep strain there that we calculate, the segments are getting smaller and smaller. And so for that one, I calculated 0.0006. Whoops, one extra zero in there. Okay. So if we add all those up, we get 0.004. All right. And I realized I didn't get my 5-minute warning, so we are at the end of class time. I hear the zippers zipping. So we'll have to do the other two methods in the next class. But we'll end there for today. So you can see 0.4% creep, not too much. So that's a good value. And that is the time hardening method, time hardening rule. All right, so one more question. That is for one cycle, yep. So now if the question asked you, we do this cycle 80 times, what's the total creep strain? Then you could calculate what it would be after that amount of cycles. So we could say that this represents that in that way, but a more accurate way to do it would be to continue following out on this time path. Sorry about the interference there. Again and again, right? So the increments of strain are going to diminish the more we go along these cycles, right? So if we go back, I just want to continue on because it's an important question. So now at 60 hours, if we go back and we start another cycle at 10 hours, see how the strain, the creep strain drops off there. So at some point, it's going to kind of diminish down to 0, right? Because now it's like, you know, tiny, tiny increments.
So you can't assume each cycle as the same?
Yeah, so I'm going to take back what I said, right? If you were doing a super conservative analysis, you could say that each cycle is the same. But because because these are logarithmic curves and they drop off the further you go up, then at infinite number of these thermal cycles, the increment of our creep is going to drop down to 0. So it's an interesting question. Excellent question. Thanks, everybody. I will see you on Thursday.